All right, here we are on this extremely miserable day. So luckily, the technology enables us to have a class anyway, in spite of the awful weather. So I'm living quite a bit further north in Purchase, so the weather's really bad up here. I don't know how it is down there. So looking out my window, I can see a lot of ice and other nastiness out there. So anyway, so normally this is something that normally has to be done once or twice, typically every winter. Um, and so the good thing about this is you don't have to leave your home. And if for some reason you can't be here, you can watch the recording. So this one will be recorded. And because there isn't that much room on Brightspace for files this large, I actually do have my own YouTube account. And in fact, during the COVID, this is how all the teaching got done. Every single class was online, and then what I would do is record it on Zoom and then put it on my YouTube account. So I have a lot of YouTube videos actually, but they're all teaching videos. So in order to find it, my the name, I guess the way you would find it is if you type in Dr. ACA. I think that will take care of it. Oops. Oh, look, I have a separate link. I didn't even know that. But anyway, that's how you find me. And oh wait, no, sorry, that's Instagram. Oh, ooh, no, let's go back to YouTube. So I think I'm already logged into my account, so it's hard to tell. But when you look for me from your account, I'm pretty sure if you type Dr. ACA, you'll find it. And so what I normally do, yeah, that should be me, is I usually try to set up what's called a playlist. You're probably familiar with that. And so that way, you can find your files very quickly and easily because I do have other classes with recordings going on here. And so in order to make sure you can find them, they're all organized by playlists. Okay. Now, I'm sure you're very comfortable with this technology. I just want to make sure that it's clear. So it isn't set up yet, this particular playlist, but it will be as soon as we're done with this recording. I'll set it up so that you can go in here. You can look in videos. I made sure they're all listed as publicly available. So you could, in principle, find it here in this enormous list, but I think it would be easier to look directly into the playlist. Because you can see, wow, there's a lot. Yes, there's a lot of them. So anyway, that's what we're going to do today. And so we're just going to pick it up where we left off the other day, which is to say, we'd started to look at section 1.9. And section 1.9 is where we introduce inverse functions. Okay, whoops. Now, I'm not sure how far we're going to get today, but we'll give it a shot. So I'm trying this experiment here where I would, instead of writing on the whiteboard, I'm going to write on a Word document. It just so happens that I have a tablet here, so I can do that. And so what I'm going to do is hopefully have the notes in the right so you can see them, and the what I'm writing on the left. We'll see how long this lasts. So this split screen thing I find is kind of awkward, but we'll give it our best shot. Okay. Something like this, you would think that I could just sit here and type it in Word, but it's because it's a math class, that's just not going to work. I'm going to do it by hand with my tablet, and it'll be just like writing on the board. Anyway, so let's begin with the inverse functions. So I think I started to mention this the other day. The best example I can think of is a function like this. Let's say you have f of x is x squared, and at g of x is the square root of x. So these two functions, as it turns out, are inverses of each other, and we'll see later on a formal way of proving it. But the logic here is this. Think of it as one is doing the opposite of the other. In fact, one is offsetting the other. So in other words, if I started out with x equals 4, and then I apply f of x to that. Oh, by the way, it is actually possible to ask questions with this system. There's a way you can, I don't know, I forgot exactly how that works, but there's a way you can ask questions. That what I think will happen is if somebody has a question, something will change color up here. And then I'll see it and I'll click it on, and hopefully that means that you can either type in a question or ask it directly. So, like technology is not my thing, but you've probably used this. So yes, it is possible to do that. So, all right, anyway, um, f of x would therefore be 4 squared, which is 16. And then if I apply g to 16, it'll bring me back to x. Okay, so in other words, think of it as one is offsetting the other. So that is what it means to be inverses. Now, here, they're giving us a slightly different case. This is a very simple function. And so because of that, they're actually using ordered pairs to represent this particular function. And hold on, make sure you can see the whole thing. Let's see, maybe I can make that just a little smaller. All right, that's good. I want you to be able to see both of them at the same time, of course. So the logic here is that you've got ordered pairs. And so the way to think about this is that in the first set, the ordered pairs of units are 1, 5, 2, 6, 3, 7, 4, 8. In the inverse function, you notice how we're reversing the x's and the y's. Okay, so in other words, so that's really what you're doing with an inverse function. You're reversing the x's and the y's so that where previously you had a 1, 5, now you have 5, 1. And they're also making the point here that for the function f of x equals x plus 4, its inverse is x minus 4. And so you can tell by simply looking at the ordered pairs. Now, if you were to graph these, you'll see later on when we do a few of the graphs that there's a symmetry between the two. So you can recognize from the graph that two functions are inverses of each other. But there's also a very powerful algebraic technique that will make it possible for us to prove whether or not two functions are inverses of each other. And then here's the graph. We started to look at this last time. They're basically trying to show you visually what is actually happening here. We make that a little bigger for you. So when we start, and this is the same example they just had, f of x equals x plus 4. So we go from the domain of f, we take our x's, we turn them into f of x. And then to bring it back with the inverse, oh, by the way, one more thing I wanted to mention here before we go any further. In our book, here's the notation they'll use to indicate that this is the inverse of f of x. Okay, so this is standard notation in math. F with a -1 superscript attached to it means that it's an inverse. So that's why it's written this way. F of x is x plus 4 up here, and then down here, f inverse of x is x minus 4. So we're working it backwards. And they also make the point here that the domain of f equals the range of f inverse, and the range of f equals the domain of f inverse. Okay, so this is a very important graph for us to remember. And they mention here exactly what I said a few minutes ago. F and F inverse have the effect of, quote, undoing each other because, that's an English word. It's not as precise as it could be, but I think you get the idea. Okay, here we go. We got some chats. Let's see. All right, so that's fine. If you're a little late, that's because this is being recorded and we really just got started. Yes, no, I've got you. Don't worry about that. And when the recording is over, I'll have a list of people who attended, even if they came in a little late. You'll be on the list. Okay. And same thing with Mark. Don't worry about it that you're a little late. The system is keeping track of who's in. So and of course, under the circumstances, I expect some people might be late and some people might not be able to get into it at all. It happens. So that's one of the important reasons why it's so important to record it. Okay. All right. Anyway, so let's get back to this. Um, now here we go. Now, here what they're going to do is show you how to prove that two functions, now this is the algebraic proof, are actually inverses of each other. So in other words, they claim in their example that the function f of x is x plus 4, and they are going to claim that its inverse is x minus 4. So the way to prove it is actually with composite functions. Okay, so just in general, to show that two functions are inverses. And let's say, just to be as general as possible, the functions are called f of x and g of x. Okay. Let me just fix that a little bit to make it a little clearer. For any two functions, f and g, let's say, we must show two things. And it has to be both, by the way. One is not good enough. Okay. So what do we have to show? For one thing, number one, f of g of x must equal x, and g of f of x must also equal x. Okay, so if you're asked to prove whether or not two functions are inverses, this is what you have to do. Now here, they're calling it f and f inverse. So let's do this. We're going to prove it. Okay. So the first thing we have to do, and remember, we just started doing composite functions just the other day. So the timing is good. So we know what this means. F of f inverse of x means that you're going to your f of x and replacing all the x's with f inverse of x. Okay, so remember how that works. Here's f of x. All I have to do is replace this x with f inverse of x. Now I have to substitute x minus 4 in here. And there it goes. It's equal to x. Okay, beautiful. But now we're not done, because we also have to show that f inverse of f of x is also equal to x. Now, once again, what you're actually doing is you're going to your f inverse function and replacing all the x's with, in this case, f of x. So here we'll end up with f of x minus 4. And then f of x, because that's x plus 4, it works. So you've just seen, and you'll see it's over here in the slides too, proof that these are in fact inverses. Now, as far as the symmetry goes, let me just see if I can get this up on our Desmos. I find that for some reason, Similar doesn't really do a good job with trying to show two graphs. Or I don't know. I think this one just tends to work better for this kind of thing. So I have x plus 4 and x minus. Um, oh, wait a minute, what happened? Oh, yes, no, they're that's fine. They're just supposed to be symmetrical. In this case, with respect to the origin. All right, for a second, I thought there was a problem. No, the symmetry would be with respect to the origin. Okay, so let me just quickly sketch it in here. But yes, there has to be a symmetry of some kind for two functions that are inverses. So let me change that to f of x. So yes, as long as you can see symmetry there, that's it. That shows you graphically that they're inverses of each other. All right. Now here's the question, big question. They gave us both functions. They said, listen, here's f of x equals x plus 4. Here's f inverse of x, x minus 4. They didn't show us how they figured that out, though. This is what's coming next. They would like us to have a way of finding the inverse of ourselves. Okay, so here's the example they're going to use. F of x is, let's say, x plus 4. And then they're saying, well, wait, sorry. No, it isn't. It's x times 4. What they're basically saying is that intuitively, it should be clear that if I'm multiplying x by 4 in f of x, I must be dividing by 4 f inverse of x, because that's how one is actually offsetting the other. But you know what? Intuition doesn't always help. You know what I mean? Sometimes intuition is right, sometimes it's not right. How do we actually formally do this? What is the formal procedure for finding the inverse of a function? Well, it goes back to this idea. We go back to the beginning, and you notice in the inverse function, the x's and the y's have been reversed. So that will give us a hint as to what we're going to do next. First, just to make this easier to follow, for this part at least, I'm going to, instead of writing this as f of x equals 4x, I'm going to write it as y equals 4x. So now, given this information, find the inverse. So it's a two-part process, and it goes like this. Reverse the x's and y's. And 2, solve for y. Okay. In other words, again, we're reversing the x's and y's. So in other words, in this case, if the original function was y equals 4x, now it becomes x equals 4y. Okay. So notice all I did was turn all the y's into x's and all the x's into y's. Well, this is a simple case. There's only one of each. But however many there are, each y becomes an x, each x becomes a y. And now all I have to do is solve for y. So that means that the original function, if that was f of x, that implies that f inverse of x is x over. Okay, now that's a very simple case, but they're all done in the same way. Now, some of them can be much messier than this, but still it's the exact same logic every time. So now what we're going to do to get some practice is we're going to prove it. Okay, so we're going to follow the same procedure that we had before. So what I have to do is go to the first function, replace each x with f inverse of x. Now make the substitution, and there's your x. Okay, that condition has been met. Now, work in this case. So go to the f inverse function and replace that x with f of x. Make the substitution. So we've satisfied both conditions. I'll put a little check mark here to indicate that we've done this And that's the proof that we've done this correctly. So for these cases, you'll usually be asked to do two things. Number one, find the inverse, and then secondly, prove that what you've done is correct. Okay. So for, let's say, any MindTap assignments you might run into, this is how it would work. The only thing that will change is that the functions will become more complicated, and then you'll just have to be a little bit more careful with the algebra. Okay. And then they're reminding us here that for these functions, the domain of f is the range of f inverse. What happened here? Oh, yes, go ahead. Nicole, do you want to ask?
So after you had, I I'm unclear what happened after you had x equals 4 parentheses x over 4.
Right here?
Right above that.
Here.
Yeah, then
Oh,
the next step after that, was what I'm not clear about.
in other words, if f equals f inverse of x, that means that what you're doing is you're taking the original function f of x, and wherever
Yeah.
you see an x, replace it with f inverse of x. Okay, so in other words, this x becomes f inverse of x. And then you substitute the actual definition of f inverse of x, which in this case is x over 4. So you've got 4 times x over 4, which reduces to x. And then for the one below it, you're going the other direction. You're taking this function, the bottom, the f inverse function, and each x is being replaced with f of x, which happens to be 4x. So when you plug in 4x there, you'll get x, which is what we're aiming for.
Hmm. All right.
Yeah. Oh, don't worry. We'll get plenty more practice with this. So anyway, what I wanted to show you down here is that the domain of f is the range of f inverse, and the domain of f inverse is the range of f. In other words, they're just the opposites of each other. And they may ask you to prove that when, like, for example, here, well, these, yeah, this, it wouldn't be a problem here because the domain and the range are the real numbers for both of these. So that wouldn't be particularly challenging. But later on, they might ask you to demonstrate in one of the problems that, have you write out the domains and ranges of the two functions and then make sure that they match up with each other. Now, here they want to remind us that with graphs, now here's some oddball function. They've made this up. You see these weird curves here. This is some oddball function, but what they want you to notice is two things. Number one, we've got for every AB up here, we have BA down here, which we already knew that. But they also remind us that there needs to be a point of symmetry in here. And it's called a reflection. Okay. So in this case, the reflection is with regard to the so-called identity function, y equals x. And in fact, now that's exactly what happened here. This dashed line here is actually f of x equals x. Okay, so there has to be symmetry between the graphs of f of x and its inverse. Oh, so they want you here to do this graphically. They want you to show a graph of 2x minus 3 for f of x, and g of x is 1/2 x plus 3. So I'll tell you what, because we could probably use the practice. Let's run through that process one more time. Suppose we didn't know that 1/2 x times x plus 3 is the inverse. Um, let's do this ourselves. So remember, the first step is reverse the x's and y's. And so if we do that, we'll end up with x equals 2y minus 3. And now solve for y. And so what I'm going to do is add the 3 to both sides, and I'll divide by 2. So what this means that it is for the function, the original function, f of x equals 2x minus 3. As we just showed, it can be written in a couple of different ways. Or you can simply write it as 1/2 x plus 3. What they want to do here is just graph them. All right, so why don't we go to Desmos and see how that works out. Here we have 2x minus 3. And then down here, we have x plus 3 over 2. So you can, and again, I can't actually draw on this website, but you can actually visualize that there's a line of symmetry through here that cuts through the origin. Yeah, it looks good here. So you can see first they sketched out all those points. So you can see, for example, we have -3, 0 here, which means we must have 0, -3 here. And then all the rest are the same. And then you've got this reflecting line. When two lines like that are mirror images of each other, we call them reflections of each other. And so the line of symmetry is the identity function y equals x. That red line is where they're symmetrical. If you were to imagine that that's like a still lake or something, you hold a graph of one over that water, you'll see the other one in the water. Okay. So now, yeah, here they're just reminding us for each point on the original function, the reverse appears on the inverse function. And that's how you can tell that they are in fact inverses of each other. Now we're bringing up a very interesting concept here. One-to-one functions. Now this gets us back to our original discussions about functions. So this is a special case. And you'll see why this matters. Why did they save it for this moment to explain this to us? So remember in the beginning, we said that you can tell if we have a function instead of just a relation because each x is associated with exactly one y. Okay, so that's a function. Now here's the thing. We also remember said something like this could also be a function. let me make this a little bit more complicated. I'm going to use birthdays as a quick example here. There's a reason for this, by the way. Okay, so here's Bill. He was born on June 6th. And it turns out John and Mary are twins. So they're both born on March the 2nd. Is this a function? Yes, because each x is associated with exactly one y. The fact that two of them are attached to the same y doesn't make any difference. It's still a function. Okay, so remember, a function means a relation, let's just put it this way, to be a function, it must be the case that each x, in other words, member of the domain, is associated with exactly one y, in other words, member of the domain. Many x's can be associated with the same y in a function, as is the case with people and birthdays. Okay, so we get this. Now, the one-to-one function is a special case. There are two things must be true, where not only is each x is associated with exactly one y, but in addition to that, each y is associated with exactly one x. In other words, it has to cut both ways. So if we come back here and look at these two examples, this one is a one-to-one function. This one is not, because two people have the same birthday. All right, does everyone see why? Because you've got y equals March 2nd is associated with more than one person. So it's a function, but it's not one-to-one. Okay, so what we want to now go on and claim here is that we can tell if a function is one-to-one. Well, first, if you recall, all right, let's do this first. Recall, we can use the vertical line test to determine if a relation is a function. Remember how that works? In other words, if a vertical line crosses a graph more than once, then the relation is not a function. Okay, so in other words, here's a case that passes the vertical line test. And this one fails. As far as one-to-one goes, we can test for a one-to-one function using the horizontal line test. So in other words, there's a vertical line test and a horizontal. With the horizontal line test, if a horizontal line crosses a graph more than once, then the function is not one. So let me show you a couple of quick examples, and let's also try to figure out why. So now, of course, we're very familiar with y equals x squared. Let's just grab a few points from this function just to see what this is all about. Here's -2, here's -1, 0, 2. This is going to be 4, 1, 0, 1, and 4. So if you try to represent this with those this type of graph, so you can see what the problem is. -2 and +2 are both associated with 4. -1 and +1 are associated with 1, and 0 is associated with 0. So while this is a function, it's not one-to-one because you can see in principle many of those y's are associated with two x's. Now we can show why with this horizontal line test. If you drew a horizontal line through a parabola like this, oh, I goofed it up. Hold on. I want to make it a little neater. Yeah, you can see. Oh, there you go. So a horizontal line crossed the graph twice. So this fails the horizontal line test. And so again, we conclude that it's not one-to-one. Although it's a function, it's simply not one-to-one. On the other hand, let's take a look at this case. And so if we were to, let's say, draw a graph like one of these little diagrams, or first we'll start with a table. Just like the other one we had. You see, each x has a unique value of y. In other words, it's not the case, for example, that -2 and 2 both are associated with the same y. They're not. And if you were to draw one of these types of graphs, you'd see the same thing. Oops, I missed one. Make these a tiny bit bigger. Oops, sorry, this one should have been -8 down here. All right, so you see what I mean? So every one of these x's is associated with a single unique y because of the fact that the negative x's are converted into negative y's, not positive y's, unlike with y equals x squared. So if you're to now draw horizontal lines through this graph, you would see the same thing. There's no way we can find a horizontal line that will cross through this thing more than once. So this one passes the one horizontal line test. So our conclusion to all this is that y equals x cubed is a one-to-one function. Okay. Now, all that is very interesting as far as it goes, but there's a reason why they brought this up right now at this point, because it turns out that if a function, oh, before I even tell you this, I just wanted, there's something I should have mentioned earlier. Not every function has an inverse. All right, that I neglected to mention when we were introducing the topic. There are functions that simply don't have an inverse, okay? But if a function is one-to-one, it is guaranteed to have an inverse. So that's one of the reasons why this is of interest at this point, because if we can prove that a function is one-to-one, we know that there does exist an inverse of some kind. Okay. Now, also, I wanted to show you an example in the real world of a one-to-one function that you might find interesting. We know that birthdays are not one-to-one because, you know, we saw this earlier. We have John, Mary, and Bill. And we saw before that the twins have the same birthday. So birthdays are not one-to-one. Or birthdays, the birthday function, let's call it this, the birthday function is not one-to-one. But here's one that is. And when you think about it, you'll say, yes, I hope this is the case. Instead, let's take people and over here, instead of birthdays, we have social security numbers. Oh, for God's sakes, let me fix that. But I think you get the idea here. I mean, we even John and Mary are twins, but they still have two different social security numbers. They have to. Everybody has a different number. That's the whole point of this. Actually, let me draw this a little differently. I just realized I made a mistake here. And so based on that diagram, and you know the way this works, everybody gets a different social security number. So the social security function between people and social security numbers is one-to-one because everyone must have a unique social security number. Okay. This is different from birthdays, where many people can have the same birthday. Otherwise, there could only be 365 people in the world. Okay. So yes, so this one is one-to-one. Now, by the way, you know what that means? If suppose that you came up across this question in MindTap and it says find the inverse of y equals x squared. The answer would be there is no inverse. Okay. I don't know if they would try to trick you like that, but be aware that this kind of function doesn't have an inverse because of the fact that it fails the horizontal line test. It's not one to one. So it anyway, so let's move on. All right, so this is pretty much everything we did. Yeah, this is the same example they're using. And so therefore, as they say here quite correctly, the mere fact that we do not have, or that we failed the horizontal line test means that y equals x squared is not one to one, and therefore there is no inverse to it. But this one, all right, this is similar to one I did. This is x cubed minus one. You can see it must have an inverse because it's clearly one to one. The fact is that it passes the horizontal line test. But not this one. Okay. So what I have a feeling is that in mind, WebAssign rather than trying to trick you and say, well, what's the inverse here? What they might do instead is say, does it have an inverse or not? Okay, I don't think they would try to be cruel to you. Um, but if you know if that pops up, just be aware that the correct answer would be there is no inverse. Now here they're going to go back, and this is exactly what we did. How do you find the inverse function algebraically? So, by the way, this bizarre function does have an inverse. You can tell by looking at it. It does have, or it does pass the horizontal line test. So it's going to be a little tricky. Oh, they did not graph them. I've attempted to graph these in Symbolab. Basically what you're going to see is something just like this, only flipped around between the two axes. But once again, they're telling us that they're going to follow the steps. In fact, why don't we do this one ourselves and prove that they're doing it correctly? It's a little messier than the other ones we were doing earlier, but we can do it. So in other words, they want us to start with y equals 5 minus x, 3x plus 2. So step one, we swapped out the x's and y's. Do that right now. X equals 5 minus y over 3 plus 2. And now we're going to solve for y. Okay. So 5 minus y over 3y plus 2. All right. Now it's going to be a little messy, but we can do this. So first thing first, let's cross multiply both sides by 3y plus 2. And then we'll use the distributive property here to come up with 3xy plus 2x equals 5 minus y. Now we need to get all the y's together into one place. So let's add this y to both sides. And then we'd like to get all the x's and constants on the other side. Subtract the 2y from both, 2x rather, from both sides. Now what I'm going to do is factor out a y from the terms on the left. Now I'll divide both sides by this expression. And there we go. This is my inverse function. So we can rewrite that as y minus f minus 1x. Oh, actually, no, we can leave it like that. We want the x's and the y's. So the original function was 5 minus y. So I think I picked, what happened? I didn't ask for that. Oh, I didn't ask for that one either. All right. So that'll do. 5y minus 3y plus 2. Oh no, 5 minus y or 3y plus. Well, I really goofed that one up. Wait, oh no, sorry. The original function was, what am I saying? It's 5 minus x. That's after reversing it. 5 minus x. Okay. All right. So what I would just like to do is quickly put these in Desmos so you can see that they are correct. Okay. So, and then 5 minus 2x divided by, uh, I forgot the parentheses. 3x plus 1. And then down here, 5 minus x divided by 3x plus 2. Oh, that's interesting. Look at that. Well, looks like the symmetry here is with respect to the like y equals negative x. Now there's a line that cuts through the origin, but with a -1 slope. So anyway, that's our final result. Now, what comes next? So I believe that's the end of this section. You go confirm that. Yes, so that was 1-9. So now we're completely done with chapter 1. So we're going to at least take a peek at 2-1. Nope, sorry, this is the wrong one. Here we go. This is 2-1. Okay. So we're going to be taking a closer look at quadratic functions for a bit. And we start by reintroducing to you a very important concept. This function is called a polynomial. It's a general name that means a function where you can see we have many terms. Poly means many, nomial means numbers or terms, but there's restrictions on what we're allowed to do here. If you notice, yeah, the ends cannot be negative and they must be integers. Okay, so in other words, if you notice what they've done here, so the way they're writing it is this. F of x equals an, which is a constant, x to the n power, plus a, and the next term, we just subtract 1 from the n. Oh, sorry. Now, you notice how the exponents are declining as we go to the right. Eventually, we'll find ourselves with 2. Then we'll have just x. Now, what they're showing you here too, at the very end, because x to the 0 is just 1, usually a1x1 is written as just simply a1x, and a0x0 is written as simply a0 because x to the 0 equals 1, if you recall. So what they're doing here is showing a general expression where n is a non-negative integer. Which simply means 0, 1, 2, 3, etc. So a quadratic function is a special case of this. N equals 2. You can see that directly from here. You're going to have a2x2 then we go down 1. And there we go. Okay. And then, of course, we can also yeah, I go through this sometimes. You got to be careful when you write with this thing that you're not going past the boundaries here. So, and then we can also say the same thing about a cubic function. Now, it gets like this sometimes. Now, we're just going to fix that. Replace it. All right, that should take care of it. Now, no, it's still anyway. A cubic function is a special case of a polynomial where n equals 3. Okay. So in other words, if you start with 3, and of course we can rewrite this as a 3x cubed, a 2x squared, a1 plus x, and then a0. And then also, there's two others we can mention here. A linear function is a special case of a polynomial where n equals 1. So that's easy. You just have yeah, there you go. That means your a1 is a slope, a0 is your intercept. And even then, you could also make the case that a constant is a special case of a polynomial where n equals 0. And for that one, all you have is f of x equals a0. Okay, so with that in mind, let's come back here. Yes, and so they changed the letters here, of course. This is the normal procedure to have ax squared plus bx plus c. We use that for the quadratic formula all the time. But also, here's some new notation here. Degree 2 means the highest exponent in the polynomial. The degree of a polynomial equals its highest exponent. For example, a cubic function is a polynomial with degree 3. A quadratic function is a polynomial with degree 2, etc. Okay. And also one more thing, if you notice, we always write the terms from the highest exponent down to the lowest. That's the normal convention. It's just easier that way. Now, with all that being said, we're going to come back and revisit quadratic functions. There's a few more details they want to add here besides what we've already discussed. So we're going to go back and revisit quadratic functions. We know that a quadratic function is always illustrated with a parabola. But there's more going on here than we may realize. For example, all parabolas are symmetric with with respect to a line, which we'll call the axis of symmetry. Now, what is that all about? Well, in this case, you notice the symmetry is from the left and the right-hand side of the axis. So the axis of symmetry is the vertical axis, which is another way of saying x equals 0. Now, there's the line x equals 0 is the vertical axis, but you might have something else going on, like, for example, suppose this is the line x equals -1. the parabola is symmetric on either side. Here, the axis of symmetry is the vertical line x equals 1. So every parabola has this axis of symmetry. And if you notice, it cuts through this, in this case, the smallest point on the graph because it's facing up. So if instead we had something like this, here the axis of symmetry is, of course, the vertical line x equals 1. Now, here's the interesting detail. The point where we cross is either the smallest or the largest value in that function. So here, for example, this point 0, 0 is where the function, which is its minimum point, or its minimum value, and down here, this is the point where the function reaches. Let's see, I can move this. Running out of space, I'm going to move this a little bit. Now I have to fix these lines. This is the point where the function reaches its maximum value. Anyway, why am I mentioning that? Because on a parabola, or let's put it this way, for a parabola that is facing up, there is a unique minimum point, and where for a parabola that's facing down, there is a unique maximum. The minimum or maximum point on a parabola is known as its vertex. So when you see that word vertex with regard to parabolas, that means the point where it either reaches its maximum value or its minimum value. And the axis of symmetry always crosses the vertex. All right, so in other words, they have to coincide with each other, that the point where we reach our maximum or minimum value is also where we have the axis of symmetry. All right, now that's interesting. And now they will ask us how to find that point. Okay. So there's a special formula for that. That vertex is, it just for whatever reason, the mathematicians have always done it this way. The vertex is referred to as H comma K. Okay, in other words, H is the X coordinate of the vertex, and K is the y coordinate of the vertex. Now, how do we identify this? Well, there's a special way to do this. If you remember from when you learned about the quadratic formula, we typically write the quadratic equation as y equals ax squared plus bx plus c. So for this vertex, okay, so the hk looks like this. All right, so in other words, once we know what that function is, uh, negative b over 2a is the x coordinate, and f of that, actually, let me write this as f of x to make it more. So in other words, there's a formula, a fairly straightforward formula that we can use to identify our vertex, taken from the actual formula, or equation, I should say. All right, so let me run a quick example by you. And I'll tell you, let me go into Symbol Lab and see if we can draw one that's really, not going to have a really hideous answer. Let's try, for example, y equals, oh, let's say x squared plus 3x minus 3x minus 2. No, that's not good. I'm trying to plan one out that's going to work out nicely. Wait, I know. Plus 3 minus. Let's try that. Ah, okay. So they're not the neatest numbers in the world, but we can handle this. X squared plus 3x minus 4. All right, here we go. So x squared plus 3x. Okay, so A is a coefficient of x squared. B is the coefficient of x. C is the constant. Okay, so negative b over 2a negative 3 halves. That's our x coordinate, or h. K is f of negative 3 halves. So we'll have, since f of x is x squared plus 3x minus 4, f of negative 3 halves is negative 3 halves squared plus 3 times negative 3 halves minus 4. Now, negative 3 halves squared is positive 9/4. If we need a common denominator, let's go with 4. Oh, sorry, that would, No, that's right, 4/4. So what does that leave us with? So that's our K. So HK is the point -3/2 -25/4. And the axis of symmetry is x equals -3/2 because that's the H coordinate. All right. So that wasn't so painful. Well, it was a lot of work, but um now of course, we're just starting this topic. So we'll definitely now, oh, by the way, here's where they're leading up to. What we can often do, you might remember that there's two different ways of writing the equation of a straight line. And the same thing is true with the equation of a quadratic equation. So in other words, there are at least two ways to write a quadratic equation. We can have f of x, as you know, ax squared must be x plus c. But you also have this other version, which we're about to look at in a second. And that's called the vertex form. I guess we can call this the standard form. I don't know if it actually has a proper name, but the vertex form looks like this. So they'll show you in the slides that it's a times x minus h squared plus k. So in our case, one we just completed, so remember a in our equation was 1 from way back here. The h was the -3/2, and the k was the -25/4. Okay, so it may not look like it, but this is the same equation as this one up here. It's just that one is the so-called traditional form, the other is the vertex form, and you can expand this out, and you'll see that they are the same thing. But for some applications, it's more convenient to write our parabola in terms of the vertex form, because you can see it just by looking at it what the vertex is. And they remind you once again that with this form, we have an axis of symmetry, and they also want to remind you that when a is positive, the parabola faces up, and when a is negative, it faces down. All right, so then they're going to have some examples, and some, now then it'll get interesting because then we're going to try to identify the minimum and maximum values with some applications. So hmm. All right, so let's see. What, this is slide 13. All right, you know what? I'll tell you what, we've gotten so much work done today. I think we can stop right here. I'll post this on Brightspace so that you know you don't, you may not have let's say had time to write down all these details. So you know, in the classroom, it's understood I have to erase the board, but here we're going to take advantage of the technology and I'm going to save this so you have a copy of it. I'll put it in Brightspace. And so that way you'll always have a copy of this thing. The only thing I'm going to do is I'm going to insert some page numbers. I don't understand Microsoft's thinking. Page numbers are not automatic unless you ask for them. It really makes no sense to me at all. There it is. So that way, if you want to print it out, at least you know what order they're in. You see, now it's got numbers. That's how it should be. Okay, so we'll let it stop. We'll stop it here. And then you can recover, and I'll see you again next Monday, hopefully in person, if this nonsense clears itself up. All right. And of course, over the weekend, you don't forget you do have mind taps too, but they're based on the earlier part of chapter 1. So you should be all set. All right. So I guess well, you know, now it's good that we had one of these sessions because, you know, with the weather the way it is, there's always a chance we might need to do this again. But I can see that it worked. We all managed to get online on time, and this is good. So, all right. So I'll see everyone next time.
Thank you.
All right. You're welcome. You're welcome. I'll see you on Monday in person, I hope.